Alright, when it comes to understanding forces, Newton's third law is actually rather essential for the entire process. So we're going to illustrate this by using a sample problem. So in the sample problem, we have basically three proteins. They're connected together by some kind of ligand, and the ligands are the little black bars connecting to them. And what you're told is they all move together as one unit. So if the microscope pulls on the end, they're all going to move together, no matter what you do or do to them. Now, where Newton's third law is required is if you take a look at this particular problem. If they're all moving as one unit, we can just pull on one end and move them all. Now, one of the things when it comes to taking things literally is you got to turn your intelligence down quite a bit. If you take a look at this particular setup, the microscope actually only pulls on the right one. It doesn't touch any of the other ones. So what you got to ask yourself is, well, why do they move? And the answer to this is they're all connected together. If you want a very concrete answer, because we have these rigid connections, on each of these elements there is going to be a pair of forces that are in opposite directions that come from these connection points. And it's these pairs these pair of forces that are going to actually cause them all to move together. If you take a look at this leftmost one, this ligand force that I just drew in pulls it to the right if I move them all to the right. Likewise, for this middle one, there's going to be two forces that act on it and cause it to move together with the rest of them. And then with this right one, again, there's going to be two forces acting on it that come to move it with the right one. So that's why Newton's third law is required. If you want a simple explanation for it, it's best done by analogy. So let's say that you're sitting out there, or you're visiting your parents' house, and your brother has abandoned his cat at your parents' house. So here's the cat. This is a rather personal example. That's about as good as a cat. And you want a cat to move. Typically speaking, you don't actually have to, move every single bit of the cat. You can just push it out of your way like this, or push it out of your way like this, and it'll, generally speaking, move together as one object. Newton's third law is what actually allows this to happen. If you push on one particular spot, if all the other spots are connected, they will all move due to these interacting forces. Now, in terms of problem solving, there's several different ways that you can approach these problems in which Newton's third law is relevant. In your textbook, what it's going to do is it's going to take each of these forces we just drew in, give them all a different variable name, so you'll have 5 of them in this particular picture, and you have to do a lot of algebra by making net force equations for each one. If that's the way you want to go about doing it, I welcome you to it. However, that's probably the slowest way of approaching these types of problems. The nice thing about having Newton's third law applying itself is it lets you treat objects in whatever grouping that you want. So if you pick up a pencil off your desk, you don't need to worry about all the atoms in the pencil. You can just treat the pencil as a single object. Newton's third law keeps that true. Now, at the end of the day, if you wanted to solve this problem very quickly, what you need to realize is that if they're all moving together, they gotta all share the same acceleration. So no matter how we choose to look at this set of 3 proteins, we should get the exact same acceleration. So if we want to do this fast, which should always be your goal, what we're going to do is we're going to change how we look at this. So I'm going to start off by looking at it as a single object. Now, if I look at it as a single object, all these paired forces here, they're going to cancel out with one another, because they're all acting on our object as a whole, but they're equal in magnitude and opposite in direction, which is a consequence of Newton's third law. So they're all going to be gone. Now, if I take a look at this thing as a whole, the only force that is not balanced out by something that's in my system is this 6 nanonewton force that's at the end. So basically here, I have a problem that has a single force. Right? So if there's only one force here, what I can say is my net force is 6 nanonewtons to the right. Now, you got to be very careful here. If I'm going to look at this as if it were a single object and use my relationships, I need to identify the mass. If we're putting them all together as one object, my mass here is 7 micrograms. Hopefully nobody has any questions about how that got done. You just add them all up. What that means is when I put this all together, I can actually find the acceleration of my system, all of it, in a single step. Now, I can take 6 nanonewtons and divide them by 7 microgram. And if I do so, the units will cancel out. Nanonewtons and micrograms, if you divide them, you'll just get meters per second squared. But if you do this, you can get your acceleration, treating the thing as if it were an entire single unit, just by using force is equal to mass times acceleration. Pretty fast, isn't it? Now, that's not what we're looking for here. We're actually looking for these individual little forces. So the question is, why did I bother doing this? The answer is because I've done this before and I know the fastest way about going about it. Let's say we want to find this first force of tension here, which I'm going to highlight in green. You only have to find one of them because these two that are in green are the same. They're equal in magnitude and opposite in direction. So what you can do here, we looked at the thing as a whole. We can then subdivide it and just look at the leftmost two. You're free to do that. Newton's third law makes it all work. Now, if you take a look at just these left two, again, these forces of tension here are going to again cancel each other out because they're equal in magnitude and opposite in direction. And for this green picture, the only force we have left here is this force of tension that we're looking for. Right? We're only considering forces that are inside our system. Now, at the end of the day, you're told that they all move as one unit. If they all move as one unit, your net acceleration, no matter how you partition them, should be the same. And this is the main trick to solving these types of problems efficiently. No matter which method you choose, you have to come up with this acceleration being the same. Now, since we're looking at this green picture here, I'm free to subdivide it however I like. The only net force is this force of tension. We'll call this force of tension 1, because it's the only one that isn't getting canceled out. You can add these two in, but they're always going to cancel each other out. And I can find, thus, force of tension 1 by finding the net force. To find my net force, I'm going to take the mass of my green system here. Let's just move this down. Right? And the total mass of my green system is 3 micrograms. And I'm going to multiply that by my acceleration. Like so. If you multiply this out, micrograms times meters per second squared, again, will give us nanonewtons. You could check it if you like. And what we'll get here is 2.571 nanonewtons. So we found the second force of tension. You'll notice here I didn't need to deal with multiple equations, multiple unknowns. All I'm doing is just subdividing my system as I see fit. Now, last up, you might notice a pattern here. We did it once, we did it twice. We can then do it a third time if we like. If we take a look at this purple picture, again, my acceleration needs to be the same for everything to move as one unit. And just like before, if I look at this purple picture, the purple net force is just this second force of tension that I'm trying to get at. I can find this force of tension 2 by again taking my purple mass, which is 1 microgram, and multiplying it by my acceleration. Let's put the directions in properly to make sure that everything's on the up and up here. There we go. Now, with that being said, you can just multiply this out. It's not particularly difficult to do. The unit ratio still holds true. So you'll be left with 0.857 nanonewtons. Right. Now, last up, you can do a sanity check. When you're dealing with this, what we can do is we can compare the forces and the mass they have to pull. So what you'll find here is it takes 6 nanonewtons to pull 7 micrograms. It takes 0.857 nanonewtons to pull 1 microgram, and it takes 2.57 nanonewtons to pull 3 micrograms. And if you take a look at these ratios are all the same. 6 divided by 7 is 0.857, 0.857 divided by 1 is 0.857, and 2.571 divided by 3 is 0.857. Now, you might be asking yourself, why am I looking at this ratio? What I'm telling you is these forces of tension have to work or provide a force that is proportional to the mass that they pull. This is the same thing as saying if the microscope's got to pull 3 units, if your force of tension only has to pull 2 units, you don't have to work as hard. And that, generally speaking, is true for every single one of these problems. So this is a method that I recommend you go about doing this. If you prefer to use a more algebraic technique, what you can do here is you can put in all of these forces. So you'll have the first force of tension. Here you'll have negative force of tension. These are 2's. You can put all these in. So here you'll have force of tension 2. And then here you'll have force of tension 1. And then you'll have negative force of tension 1. And what you can do is you can put every single force in and find the net force on each object using the algebraic constraint that their accelerations are the same. That method will also work, but this one here is quite a bit faster. And so what you want to take away from this is if Newton's third law is true, you can subdivide solid objects however you like. You can look at them in any partition or any grouping that you choose, and the net force equaling to mass times acceleration and also equaling to all the forces added together will still always hold up. So nothing has changed in that regard.